Okay, today we're going to look at some more trigonometric graphs. We graphed the sinusoidal functions sine and cosine and got the actual sine wave, we call that, or cosine wave. And it has so many practical applications that I can't do it justice. Sine and cosine are studied because electricity is a sine wave. Earthquake vibrations are a sine wave. Anything that creates resonance vibration is a sine or cosine wave. We already talked about audio waves. Ultraviolet rays can be looked at as waves as well. There's just so many electromagnetic waves. So these, on the other hand, these graphs are more generic, much less applicable to real life, and even in physics you won't really run across these. This is more information more than anything, and graphical analysis than it is practical applications. So we graphed the other two, sine and cosine, but we didn't talk about tangent, cotangent, secant, and cosecant. Honestly, they're not that interesting as far as what we can do with them physically, but they are interesting to look at from an assessment standpoint. So we're going to look at some graphs of these, and I know your notes are probably going to be a little scattered from this video because I'm going to skip a lot of stuff. The first thing that we have to understand is that if sine and cosine have a period of 2 pi, then so do secant and cosecant, because they're both 1 over sine and 1 over cosine. So this is very familiar with what we did the other day then. Now, tangent and cotangent, though, they have a period of pi. And that's because they don't exist at, let's say, like tangent doesn't exist at pi over 2, 3 pi over 2. Remember, odd multiples of negative, or of pi over 2. Odd multiples of pi over 2. They don't work. Now, cotangent, they don't work. It doesn't work at any interval of pi. So that's why every pi we get all of tangent and cotangent, depending on where it's shifted. Okay. So the first thing, we're going to look at tangent, and we're going to look at tangent on the interval negative pi over 2 to positive pi over 2. And when we start making a graph of this, the first thing we would do if we were going to physically do it is make a table of values and use our calculator. Well, the tangent of pi over 6 was radical 3 over 3, which is about 0.58. Tangent of pi over 4 is 1. Tangent of 0 is 0. Tangent of pi over 3 is radical 3, which is 1.73. But then we can talk about these as we get closer to pi over 2. We see that the numbers just absolutely take off for the value of tangent. Similarly, that works if we go the other direction, negative pi over 2. And that's what we end up with our tangent equation, or a tangent graph. So if you would, please, turn on your calculator, go to mode, make sure you're in radians, because radians make the best graph, and type in tangent x, and then on your window, I need you to put in negative pi over 2 for your x min, and pi over 2 for your x max, pi divided by 2, and your scale, let's just make it pi over 4 for your scale. Your y min and max, you might want to go, I don't know, like negative 10 to positive 10, let's say, by ones, and hit graph and see what kind of graph you get. It looks exactly like this. So x, we're going to go negative pi over 2 to positive pi over 2, and then our negative 10 to 10 for our y value by ones. So we get this nice tangent graph. Now, that's one period, and notice the period is pi. But if we really want to look at what this would look like, hit zoom 7, and we see this going on. Okay? But remember, every odd multiple of pi over 2 is a vertical asymptote. It doesn't exist there. Every pi over 2, we have vertical asymptote because pi, or tangent, is undefined. So this would go on to negative 3 pi over 2 and positive 3 pi over 2, and we get these graphs, the same exact graphs. So that's what you're seeing on your calculator. Everywhere you see an opening, if you draw a vertical line there, those are odd multiples of pi over 2. Okay? And there's the graph if you would go from negative 3 pi over 2 to positive 3 pi over 2. There would be three cycles. Now, it also talks about, vertical asymptotes. Yep, we just talked about those, odd multiples of pi over 2. Perfect. Now, look at cotangent. Now, cotangent is 1 over tangent. So this would be the exact same idea that we had before, except now, obviously, we're going to have problems at 0 and pi and negative pi. So type on your calculator 1 divided by tangent x. Type that in on y equals. And then go to your window, and we're just going to go 0 to pi. So 0 to pi for your x. And let's go by pi divided by 2. And then on your y-axis, let's go negative 10 to 10 again by ones. And then graph it. And you will see that graph. We're a little flatter here because we went negative 10 to 10. You probably change your window and go like negative 4 to 4 maybe. See what that looks like. Yeah, that's a little more like the picture on your sheet there. Okay, but notice cotangent doesn't work at multiples of pi. So if you go to your calculator and hit zoom 7, it will give you a bunch of cycles of cotangent. And notice it's interesting that cotangent is a, decreasing function, whereas tangent is an increasing function. Not that that's neither here nor there, it's just interesting, because really all we're doing is analyzing graphs, guys, today. Okay, so we talked about cotangent and tangent. Now these are really cool, all right? Let's do cosecant, which is 1 divided by sine. Well, first of all, let's do this. Graph sine x again on your calculator, please. Sine x, zoom 7. We get this nice graph. Okay, this nice sine wave, just like this. Now go to y equals and do the same thing, but hit 1 divided by sine x right underneath it. So keep your sine x and go 1 over sine x. So this is our cosecant graph. Now, how cool is that? It's really cool if you have a color calculator, because red and blue is what mine defaulted to, which is interesting. Now notice that cosecant, remember this is cosecant. Cosecant has vertical asymptotes at pi and 2 pi and negative 2 pi and negative pi and 3 pi and so on. And why is that? Well, because sine is 0 at all of our pi's. And cosecant is 1 over 0, which is undefined. So therefore, it doesn't exist at multiples of pi. That's awesome. That's really cool. Now, notice that the sine of pi over 2 is 1, and so is the cosecant. And the sine of 3 pi over 2 is negative 1, and so is the cosecant. But notice, the cosecant never is more than negative 1, or I should say, it's never negative 1 to 1 in between here. It is never equal to that. I think that's really cool. So that's what the cosecant graph looks like. And if we did a whole bunch of them, oh, and that's secant. Well, let's do secant. And you can bet that secant's going to look the same way. So change your sine to cosine, and change your 1 over sine to 1 over cosine, and hit zoom 7, and you're going to see the secant graph. Excuse me. Now notice that cosine is 0 at pi over 2 and 3 pi over 2. X is 0 at those two. So that means, that the secant is undefined at every odd multiple of pi over 2. And you can see on your calculator looking at it that you have vertical asymptotes at all of those pi over 2s. And I think the best thing you can do is just look at your calculator. It really makes a lot of sense. But again, notice that the cosine of 0 is 1, and so is the secant. And the cosine of pi is negative 1, and so is the secant, and and so on. So that's kind of what we're looking at with secant. So that's really the tangent, the cotangent, the cosecant, and the secant graphs. Now, we can also do multiple things with these. And we can talk about their domain and ranges. So if I go back to sine, so if you just go to your sine quick and delete everything on your calculator, excuse me, type in sine x and hit zoom 7. You can see that the sine's domain is everything. No restrictions. And the range is negative 1 to 1. Now do cosine. And hit zoom 7. I'm used to hitting zoom 6, and I hit zoom 6. I should hit zoom 7 for trig. There we go. You can see also that the domain of cosine is negative infinity to infinity, and the range is negative 1 to 1. Now do tangent. Well, you can see then that the tangent is all real, the domains, except odd multiples of pi over 2. You can see that on your graph. Each one of those little X notches here on your graph, each one of these is a pi over 2. That's pi, that's 3 pi over 2, etc. Negative pi over 2, negative pi. So all those pi over 2s you see are going to be vertical asymptotes. And then you're getting your tangent in between. Okay? But notice also that the range of tangent is negative infinity to infinity. If we look at 1 divided by tangent, which is cotangent, we see that, where's cotangent? There it is. We can see all the multiples of pi don't work. So the domain of cotangent is all reals except multiples of pi. But we can see that the range is negative infinity to infinity. Okay, now go to 1 over sine, which is cosecant. Graph that. And you can see the cosecant, oh, this range is wrong, isn't it? That range is wrong. All reals except odd multiples of pi over 2. Again, the pi over 2's don't exist. Wait a minute, secant. There we go. Except multiples of pi, that's secant. Wait a minute, I might have these all typed up wrong. What'd I just find? Cosecant. Cosecant, all reals except odd multiples of pi over 2. Let's see. The sine of pi over 2 is 1. No, this should be all reals except, ooh, that's a mistake. All reals except multiples of pi. There we go. And then, sorry about that, now we're fixing it. Now what's the range? Well, the range is negative infinity to negative 1, union in its bracket, 1 to infinity. So between negative 1 and 1, it doesn't exist, cosecant. So then secant is 1 over cosine, zoom 7. And that is all reals except, let's see, odd multiples of pi over 2. But again, the range is negative infinity to negative 1 bracket union bracket 1 to infinity. Okay, so we got to make sure and clean that up. Those are wrong. But looking at the graphs, we can definitely correct them. That's what's nice about it. Now, the rest of this investigation is all on your calculator. And we're going to be able to manipulate and transform these. And I'll be honest with you, we really never do this outside of just playing with this. So our two equations for tangent, we have a k there. Now remember that the period then would be pi over k, just like it was 2 pi over k for sine and cosine. So if we're going to manipulate this a little bit, one complete cycle would happen in a period of pi over k. So let's see if we can find a graph. How about y equal tangent 2x? So type in y equal tangent 2x, zoom 7, and let's look at the graph. Okay, now notice then, our period would be pi over k, which is pi over 2. Well, we have a million of these, do we not? I mean, they are just squiggle, 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 squiggle. Well, that makes sense because we've shortened the time period. Now on B, we're going to do the exact same thing, but we're going to shift it over pi over 4. So let's see if that has any effect. Keep the same graph, by the way, and go down below and type in tangent 2, open parentheses, again, x minus pi divided by 4. And let's see what kind of action that has on it. You see how it's been shifted? So we have the graphs. This is great. So it's the same graph, it's just been shifted pi over 4. So it's the same exact shape, but it's just moved over pi over 4, which we have red, blue, red, blue, red, blue. It's pretty cool looking on your calculator. So there's tangent 2x. There's tangent 2x minus pi over 4. It's just been shifted over. Cotangent. See what that does. Y equals 2. Okay, so it's 2 divided by tangent. So to put 2 divided by tangent, parentheses open up, so that's good. 3x minus pi divided by 4. Three x minus pi divided by 4. Okay, now we got to close parentheses twice, I believe. Oh, no, we don't. Just once. And then we could do what they did here by taking out a 3 and know that it's pi over 3 would be our period with a shift of pi over 12. Not that big a deal. We're just graphing it. And we get these curves that are almost straight lines. So that's pretty cool. But we can see every pi over 3, we have a vertical asymptote. Okay, and I'm not worried about the intervals and all that good stuff. There's the graph, and we looked at it. Now, secant and cosecant. 2 pi over k, just like we had before. So this one, on A, 1/2 cosecant 2x, we're just going to take 1 divided by sine 2x. And hit zoom 7. Now, the period then is pi, 2 pi over 2. So we get a bunch of these, but they're thinner. And they're faster because we've shortened the period to just pi. We can do the same thing with cosecant. So 1/2. Oh, no, let's do this. 0.5 divided by, 0.5 times, no, it could be 0.5 divided by, yeah, cosecant, which is 1 over sine, okay, wait a minute, 0.5 over sine, there we go, 2x plus pi divided by 2. Yeah, there we go. Zoom 6. And we get a weird looking graph. Period's just pi over 2, or 2 pi over 2, which is pi. And it's been shifted over left pi over 2. And it should look something like this. And I'm trying to see if mine does. Whoops, I must have typed this in wrong. 1 over cos. Oh, yeah, no, that's right. We shifted it over pi over 2. Yep, that's what mine looks like right there. So yours should as well. Let's do secant quick. 3 divided by cosine 0.5x. That's the way I would type it in. 3, I would type it in this way. 3 divided by cosine 0.5x. That's equivalent to that. Zoom 7, see what kind of graph we get. Barely see it, right? I only get 3 little, I get this, this, and this. Now let's look at y. Well, the period is 2 pi divided by 1/2, which is 4 pi. That's y. So 1 period is just 4 pi. So that's why we're not going to get much. And the 3 means that we've spread it out. Oops, our axis is farther away because remember our amplitude's 3 for our cosine curve then. So it's going to look like this, right? So that's why it looks the way it does. And there it is. And that is the lesson on graph.